Thank you very much, Nicole, for the kind introduction and explaining the agenda and objectives, and that we are a Swiss, a country with experience in heat pumps. So my talk here is to explain you and give you an introduction into a guideline how to integrate industrial heat pumps and especially high temperature heat pumps. So the guideline shows a little bit market context in Switzerland. Then we go to some technologies and demo cases which are realized and available. We show some integration concepts. We apply pinch analysis as an energy analysis method, and we have preliminary assessment checklist that can be followed as a guideline for integration. Then there are technical, financial, and socioeconomic aspects, which will also be covered shortly. And so in Switzerland, we have objectives for a climate neutral Switzerland by 2050. And heat pumps are a key technology to achieve these net zero goals, and especially high temperature heat pumps for process heat decarbonization. So you see here in Switzerland, 1.5 million heat pumps are expected by then. We will expand our thermal grids as well, and in general, efficiency in industrial processes should be improved. But in Switzerland, we have special situation. It's a country which has a lot of mountains, let's say. So, and the cities are close to industries. So this proximity has some challenges. So on the residential area, it has challenges or impacts on regulation, on environmental topics, safety, comfort. Then we have a special industry mix. So food and pharma and biotech are quite strong in Switzerland compared to other countries. We have a democracy with multi-layered regulatory, so the state or the national level, the canton level or the region, and then the municipality levels. So it's quite complex and a lot of regulations are there. Then we have a subsidy landscape to support renewable energy technologies, and this also includes heat pumps. So this has also influence in Switzerland on the market, and especially we have a CO2 tax on fossil fuels, and this needs to be considered in economic calculations or estimations. At the moment, it is 120 Swiss franc per ton of CO2. Now, process heat, so we look from a top-down approach. In Switzerland, about 54% of the energy in industry is for process heat. And when we look at the sectors, we have here the red bars, which are mainly here, as mentioned, chemical, pharma, food, and so on, cement, bricks, and so on. So these are the target industrial sectors to decarbonize process heat. When we look at the total process heat and would assume that 30% is below 150 degrees, which would be accessible by high temperature heat pump technology, and assume that 40% would convert to heat pumps in the future, this would give at the end about 6.5% of total process heat demand that would be covered by heat pumps. So this is a rough estimate to see which part of the process heat could be covered by heat pumps. So we have different technologies. As a guideline, we have electrical driven heat pumps, so running with a compressor, running with electricity, and in the future, hopefully, renewable electricity with a low CO2 emission factor. But electrical driven heat pumps or these vapor compression heat pumps can have different cycle designs. So here is a simple cycle, a basic cycle with one compressor, one condenser, a valve, and an evaporator. But it could be an economizer cycle, multiple cycle, cascade cycle, transcritical cycle, a Joule cycle, Stirling cycle, MVR, mechanical vapor compression included, and so on. Then we have thermal-driven heat pumps, where we run the heat pumps with thermal energy, so waste heat as a driving energy. So these are the sorption heat pumps or the sorption heat transformers. And so, yeah, the efficiency of these technologies is shown here, and we have some rough COP values that could be used in these different technologies. We will mainly focus on electrical driven heat pumps in this guideline because we think this has more application potential and there are more suppliers, and yeah, it's driven by electricity, but I would not say that thermal driven heat pumps are not important. So it's just a question of focus. So here is a market overview of these electrical driven vapor compression heat pumps, which supply temperatures higher than 100 degrees. We have shown this graph many times. It is also shown in Annex 58 in that project. The message here is that such heat pump technologies are available. Some are in a high, most of them are in a very high technology readiness level. They are in demonstration state, and so another question is the refrigerant type. Here you see the typical refrigerants used in these technologies. So there are compressors with compressor technologies with screw compressor, piston compressor, and turbo compressors mainly, and different capacities. So from the Annex 58, we have made a list of realized demonstration cases, and here is a summary of 18 of such cases. The blue ones are for steam generation. Then we have here green for drying processes. This one is for process hot water generation, and these ones for drying. Sorry, the other was the green was thermal separation. So these were the major applications, and we can say in summary, so the conventional heat pump cycles go up to, let's say, 138 degree. With MVR technology, also 211 degree Celsius was achieved here in an example, and with the Stirling heat pumps, 183 degrees. So these are examples which are higher than 100 degree. So the COPs, we have some COP indicative values shown here. So for the closed cycle heat pumps, the COP follows such a line in function of the mean temperature lift. And for these different examples of demonstration cases, when you look at MVR cases, they have higher COPs, achieve higher COPs than the closed cycle heat pumps. In average, these cases have a temperature lift of 65 Kelvin and a COP 3.9. When you look at the technology, we have to select a technology that fits the application, and the application, the industrial application. So the temperatures are important, the inlet and outlets on heat sink and heat source. And then there are applications with large temperature glide, so different large temperature differences, for example, on the heat sink, for example, for drying processes to generate hot air for drying. Then such cycles like single stage or cascade transcritical cycles would be a suitable heat pump technology, or a Stirling cycle or reverse Brighton cycle or Joule cycle. If the application is to produce hot water, then we have the typical or the classical heat pump cycles, closed cycles, also as cascades, for example, but also transcritical CO2 cycle is suitable, or a hybrid absorption compression heat pump. If you look at applications where the goal is to generate steam, then we have these types of heat pump concepts or heat pump cycles. We have a direct steam generation heat pump where the condenser is connected to the water, and it's generating steam in this condenser. Or you have a cycle with a flash tank where water is flashed and pressurized hot water is flashed, and so steam is generated. Or we have a combination with MVR to recompress a low pressure steam to a higher pressure steam. So we call it also sometimes combined cycle. Or we have a concept where we have water only as refrigerant, where the evaporator is at a high temperature, so that water can be evaporated directly. So different applications means different heat pump technology or different heat pump concepts. And so we have a first check. When we go to an industrial company, we ask them some questions. Is there a heat demand, and is it already optimized? If yes, then we go to the next step. If not, then we would reduce the demand and try to do that first before going to energy efficiency measures. Then the second is there waste heat demand or a source available with a sufficient heating capacity? If not, without heat source, a heat pump cannot be implemented. So it's very, very important that we have a heat source that is available. So the third is it available at the same time of the heat, like the heat demand? If not, then simultaneously if it's not simultaneously available, then we need some heat storage or some storage equipment. If it is available, then we need to check that the heat is so the temperatures of the waste heat and the demand, if they are in a certain suitable range. So the temperature lift should be in a suitable, meaningful range. If not, then we need to check if direct heat exchange is possible, or probably a heat pump is not required. So a simple heat exchanger would do the job, let's say. But if the temperature lift between the heat source and the process is smaller than 50 degrees, then we can go further. If it's a very large temperature lift, this gives very low COP, low efficiency, so the payback will be a challenge. And then the operating hours is another question. It's always good to have long operating hours, which is in favor for a heat pump. And if not, then if there are a lot of fluctuations and low operating hours, this will also influence the payback. And always we can go back and have a feedback loop to check the starting conditions. So this can be discussed more in detail, all this graph, but these are the main feasibility check questions and answers. Then if a heat pump would be a possibility, then we need informations on the temperatures on the heat source and heat sink, the capacities, then also the flow rates and the medium. Is it water, steam, air, and so on? Operating hours. We need some economic parameters like the costs for the electricity to run the compressor, then the costs for the other energy carrier that is used today, for example, gas or oil, and maybe also there is some additional cost for the source. Maybe it's a district heating network that would be also costly, this heat as a source, or if it's waste heat, it's almost for free. So these are questions that need to be clarified at the early beginning. And there are additional inputs depending on the industry, what application, location, the location on site, the distance between source and sink, then the available electrical power supply, and so on, and further information. Then we can do a first economic check with all these parameters. We have information of the investment costs for a heat pump based on offers from heat pump suppliers. We need information a little bit on maintenance cost, installation factor, planning. Then we need information from the application, the temperature lift, which gives the COP or the efficiency. So it needs to be a meaningful temperature lift which gives a certain efficiency because it goes directly into the operating costs or the electricity costs. So then there we have the operating time, the electricity costs, the capacity of the heat pump. That is very important. So the size of the heat pump, the heating capacity. And then if we compare it with a gas boiler, the gas costs and the efficiency of the gas boiler. Then we have maybe some compensation of CO2 tax, and this is in favor for the heat pump if we have a low CO2 emission electricity available. And all in all, this gives some calculation, a rough estimate of a payback time. So then another consideration is the integration level of the heat pump. If it makes sense, you can integrate in different levels. On the process level, this is the deepest integration. On the unit level or utility level or sector level. And this has different aspects to consider. The more complex is process level integration. This is but also the most efficient one. And yeah, that's also important. Then we go to energy analysis. Here is an example of a pinch analysis. So we look at streams that need to be heated up and cooled down in an industrial site, and we make the composite curves of these hot and cold streams. And by pinch analysis, you can find out how much energy can be or how much heat can be recovered between the streams, and what hot utility and cold utility needs are necessary. And by using these curves and make the difference of it, we can find out the pinch temperature. In this case here, around 70 or so degree. So a heat pump could be integrated between across this pinch temperature. And this would be shown here. So here, the condenser of the heat pump would be here at the 75 degree, the evaporator at 30 degree, for example. And then this would work and would be an energy optimal integration for a heat pump. It's a very simplified example, but it shows the main rules to integrate the heat pump across the pinch. So not to cool hot streams above the pinch, and not to heat cold streams below the pinch, and avoid heat transfer across the pinch from hot to cold. So these are considerations. In Switzerland, we can do pinch analysis with some funding from Swiss Federal Office of Energy. This graph shows that a lot of effort is needed before doing actually the pinch analysis. So there is pre-analysis and data collection. This is the major work to do. Based on that, a pinch analysis can be done, and then measures can be derived from this pinch analysis. So the collection of data means to understand what processes are heated and cooled, and what energies and what temperature inlets and outlets. So overall, such an analysis can take 3 to 8 months, and we need experts to do it. So some educated pinch analysis experts to do this analysis. In Switzerland, we have funding and subsidy, and it is a two-phase approach. This means there is a possibility to do a first analysis, a pre-analysis, and if it comes out that it is meaningful, a more detailed analysis can be done. And so here you see how the financial situation looks like. So a total cost for us, so a pre-analysis is between 10,000 25,000 Swiss franc. A detailed analysis can go up to 80,000. And Swiss Energy is funding here 60% or 40% of this project. And the company has to pay somehow the pinch expert, and also but can bring in some in-house services. So it's a one-by-one decision about that. But it is very recommended to do this analysis, and many companies do it, and it's very pushed also in Switzerland, to do this pinch analysis. So applying this pinch analysis means you need to represent these composite curves, so to do this analysis, find out how much heat can be recovered, find out what is the pinch temperature to possibly integrate a heat pump across this pinch. We should check if there is maybe some heat exchangers not placed correctly, obviously, and then analyze these grain composite curves and check the relevance for integrating a heat pump. Then we can also extract some grain composite curve segments for later interprocess heat integration analysis. And then in stage B, this is then the representing really the analyzed situation and maximum potential heat recovery and heat pump integration. So these are really then the experts doing this analysis. Now a few last slides on technical, financial, and socio-economic aspects. So first of all, the technical aspect. So we know after some time of analysis what would be a possible heat source, at what temperature, and at what heat sink. Then we can find a possible operating point and check if some heat pump suppliers can provide such a heat pump in this size and working in this temperature range. So we have operating maps of the heat pumps and check if the heat pump can work. And the COP is determined by these temperature conditions. Here we see as an example some COP maps for a certain second law efficiency. I think 50%, and this at different temperature glides on the source and sink. So this has to be checked. This the technical feasibility, the heat pump suppliers, and the COP. Then we need to check infrastructure requirements. So at site location, what is the situation? Okay, the distances, power supply, network, storage, automation system. Then you need to check safety aspects, the refrigerant or redundancy strategy, and different standards. Standards can be for the refrigerants, the chemical risk reduction ordinance, but there can be major accidents, so protection for that, air pollution control, explosive atmospheres, pressure equipment directive, and insurance also directive. So these are different aspects. For the refrigerants, we see more and more natural refrigerants and HFOs with very low global warming potential. These are the major refrigerants. And okay, then maintenance aspects are important to consider, and also maybe a technology lock-in where for example, gas boiler, oil boiler are already there. And yeah, so it's a retrofit situation. Then another aspect is financials, and then the funding programs are important to push industrial heat pumps adoption, market adoption. In Switzerland, we have several possibilities, and so the pinch analysis, as I mentioned before, is a possible, is a method to do the energy analysis, and it is funded with certain percentages, up to 60% in pre-analysis and so on. Then Energy Schweiz is also giving a subsidy. And then there is climate bonus and also pilot and demonstration projects. Here we are not sure if this is really going further in the next years. I hope there will still be funding possible. But there are some possibly other fundings. This needs to be checked in this particular case and a particular location. Then socioeconomic aspects. There are factors that are favorable to push heat pump technology. So with the net zero targets, there must be a very steep adoption of heat pumps into the market. So this means there must be a push, some drivers, and the favorable market conditions are when there is a lot of innovation and research and support, when there is more information, when there is economic incentives like these subsidies, if we have awareness of the technology and commitment to sustainability, decarbonization, and involvement of various stakeholders. So these are factors that help to push heat pump technology adoption. We also did a survey in a workshop in Switzerland, and here are the major drivers for heat pump adoptions. Some are more short-term drivers and the others long-term drivers. So in the short term, so is an internal analysis of energy efficient potential. If we do, for example, a pinch analysis, and we find out, okay, there is a possible integration point for a heat pump, this is a very much a driver to initiate such a project. On the long-term view, this is more, let's say, strategic orientation towards sustainability. So net zero goals, then cost savings for sure are long-term drivers, and see carbon footprint reduction. So many different possible drivers. This was the outcome of this survey here. So from development perspective, from Annex 58, we see, or we concluded there that in the next years, 27, 28, 29, so in the next 5 years, there will be in several cases, in several capacities and also temperature ranges for high temperature heat pumps, the technology developed and established. So we think that it's now time to go in to check this technology and do studies for the integration. So as a summary, it's coming all in all here. So with heat pumps, we can do energy savings, achieve energy savings and CO2 emission reductions. The guideline is for the integration people, which is engineers, technicians, maybe also managers, but also important planners. So they need guidance how to integrate, and so we should develop more and more guidelines, planning guidelines for that. So there are different integration levels, which makes it a little bit complex to integrate such heat pumps, especially in process level. On a sector level, it's easier, and so on. So we have developed a checklist that should be checked at the beginning for preliminary assessment. We always encourage to do and apply pinch analysis to find out if heat pump integration makes sense, if the heat pump is a possible measure. So we should consider the principles and practical applications. We should consider costs, funding, okay, then the economic calculations, and always have a look into the future, and also check if some new heat pump suppliers and other market trends are available. So that's from my side, for this guideline.